Good morning, everyone, and good morning to the participants in the online as well. So today is the third session of the GIAN course, which is like we are discussing on the MOF, and we will be studying more with the Professor Vittal's presentation. Yeah, sir, please.
Oh, thank you very much. Good morning, everybody. First of all, thank you very much for feedback from some of you. Let me try to go pretty slow today. Okay, I didn't realize that. Sometimes I get carried away. Anyway, if needed, we can do some of the things if you don't understand. I know later during tutorials. Okay, we'll open it up and you can ask questions. Okay, today let me summarize what we have done. We talked about, of course, we finished now about the design, and then we started learning about coordination polymer, aka MOFs, metal organic framework structures. And we continued in the last 2 hours, which I hurried up, on porous coordination polymers or MOFs, some of the magnetic properties of those. The important thing is, of course, magnetic ordering, but at very low temperature. But pin crossover is the one that has been studied extensively using MOFs. Of course, luminescence and sensing, some nonlinear optical properties. For that, you need to have a special type of compounds crystallized in non-cytosymmetric space group. All these conductivity studies and the way you prepare the compounds are completely different for proton conductivity and the electrical conductivity. Okay, one is ionic, the other one is neutral. And then how one can use MOFs for lithium-ion batteries. And again, for lithium-ion batteries, many people use MOFs as anode material, not as cathode material. Not many work has been done, and we try to understand how MOFs can also be used as cathode materials. Of course, again, for having MOFs to exhibit ferroelectric properties, ferroic properties, we have to crystallize in a special space group or point group, what is called polar point group. Polar point group. And then it exhibits very, very interesting properties. Of course, I thought I included birefringence. If I removed it for some reason, I can put it back and talk about it later, which I plan to do. Anyway, and then negative thermal expansion. And then before we talk about processability and chemical reactivity, you have to help me. Okay. So it is working. I pressed at the same time, so it moved by 2 slides anyway. So before talking about it, I will touch upon a couple of things, maybe later. Because whenever, you look at the literature, MOF5 has been studied extensively. So if you look at the number of papers cited, and the number of papers working on MOF5, enormous. They try to bring it to the market, in fact, but it is unstable. MOF5, hydrolytically unstable. So they try to circumvent this, and Miyagi was working with big companies, and they were trying to make it in kilogram quantities every day for gas option. At the same time, this HKUST is another MOF developed by Hong Kong University of Science and Technology by my friend here, Ian William, and his student, Stephen Chewy. And this is the only, usually whenever you started making a MOF from a university, you try to put in not as MOF 1, 2, 3. Only Yagi does it. For others, they put their university name and then 1, 2, 3. And as I mentioned to you yesterday, it stopped with 1. And after, he started working on something else, and now he's a senior lecturer at the US. And see, the interesting thing, why I want to talk about it, this is as good as MOF, much better than MOF. Easy to make it, hydrolytically stable. It shows better performance than MOF5. So a lot of people started working. In fact, behind Yagi, they always say that HKUSD is much better. Okay, so that's why, this particular one is made out of copper and trimesic acid. Okay, trimesic acid is 1,3,5 benzene tricarboxylate. Okay, it forms some kind of three-dimensional network structure. We can talk about it if you're interested, but it has been cited heavily. Apart from that, there are a lot of efforts, made in different directions of not I wouldn't say applications, some properties. They want to find new properties so that they can find new applications. It doesn't mean that it's going to replace the existing one. Okay, any material you make it, you really want to study and look for new properties and then see whether this can be, this can find any applications in that field. That's what we tend to do. So edible moth, I'm going to talk about it. I mean, if you can make out of edible things, of course you can eat them. And then liquid moth, again, it's a kind of, well, how can moth should be a solid? How can you have a liquid moth? I'm going to talk about it. And then amorphous gel. This is what I'm going to talk about it today. And then I'll touch upon these two maybe later. I think so make it more interesting. Yeah, thank you. Next slide. Processability. See, whenever we say MOF, immediately that comes to our mind is highly crystalline. It's a solid. Okay. I mean, of course, porosity depends on how you make it. But many people would like to make processable because once it is crystalline, it's not processable. It's very difficult to melt it. It will decompose before it melts, right? That's a general properties of MOF. They are insoluble. So for processability, you need to make it soluble, or you make it, in a different way. It has to melt. Then you can form different shapes, thin films, and everything. That's a problem they are facing in using it as a membrane for separation technologies and removing water from seawater. This is the thing. They need to make a membrane, single layer membrane of this, which is going to be a challenge because it's highly crystalline. A lot of people are working on that, still working on it. So if you want to, if you try to do some research on the processability, then you can make it into thin films for various applications. This is one of the reasons why people started working on it, and they try to make non-crystalline. Of course, just like organic polymers, you can make gel. If you can make gel, it's easy to process. Gel, fiber, nanofibers, and other different types. Even you can make amorphous compound. Then you can amorphous, and then you see any of this can melt. Then even if it is crystalline, you can melt it and use it for various applications. I'm going to highlight a couple of examples for and maybe few more. Okay, on processability. This one is a coordination polymeric gel that was reported. Okay, the thing is given here. This is the compound cobalt based on triazole. This is lipophilic. That's what they say. Lipids. This soluble in lipids because of the long chain you see. So you can put it in chloroform. When you dissolve this particular compound, easy to make it, put it in chloroform. What happened at room temperature? It forms a gel, blue gel. Although the color is green. Okay, I mean this is the Jack's paper. Okay, we need to trust. Okay, so although they show maybe it's a printing mistake, they always say it's blue because this cobalt is supposed to show. Otherwise, it looks like copper. Right? It is cobalt. Trust me. Okay, we verified it many times, but I haven't contacted the author. But we put this one. This is a blue gel. They got it. This is at room temperature. When you cool down to 0, then it becomes liquid. The color changes. Do you see any unusual thing in this part of it? Exactly. That's why I want to show this. Usually the thixotropy, when this liquid becomes like gel, you need to cool it. You are right. And then we say that this is thixotropic property. Okay, you can measure viscosity and other things. There are so many things you can do with that. And this is an unusual thing. And they themselves mention in the paper. So on cooling, it becomes, they try to explain what is really happening. At room temperature in gel formation, it forms one-dimensional coordination polymer that you can imagine. So when you heat it up, it's broken into oligomers, monomers and oligomers. And that need not have to change the color, right? So the coordination number has changed. And it is coordination number 6, tetrahedral in this blue gel. It becomes octahedral in pink. That's what, according to them, this is what is happening. So the color change is accompanied by, this particular phenomena of cooling and heating. So this is again very unusual. It works the other way. This thixotropic property. The second one is the work again, earlier work only on coding. There are so many other papers. This is by Hiragawa, and he made two-dimensional coordination polymer as a background. He made 2D polymer again with triazole. Okay, he made imidazole and also triazole. Yes, two different things. It's phosphate. He used to talk about this in many plenary lectures before, about 5 to 10 years ago, not nowadays. Because of the unusual property. Because when you take this highly crystalline compound, which has got 2D structure, when you heat it up, it melts. It melts. Usually all the morph will decompose, whether it is deep coordination polymer or 2D or 3D, they tend to decompose. It melts, it becomes glass. Okay, so this is unusual. So once it becomes glass, they try to show that the structure is retained in the melt as well as in the glass by X-rays and other experimental techniques. They try to show that the same structure 2D is maintained in all these things. They didn't decompose or anything. Okay, this is very unusual anyway for processability. So once you know how to melt it, then you can make it into different shape. You can even make it into thin films, and those kind of applications is inevitable. Well, it's obvious. Sorry. Yep. Okay. What other things you can do with processable or non-crystalline MOFs? Another application. This is published by Chad Mitkin from Northwestern University. His postdoc, he's in Korea, publishing a lot of interesting papers. So what he did was, he was making polymeric micro and nanospheres. Polymeric micro and nanospheres, they're all amorphous in nature, completely amorphous in nature. The size is about, he was able to control, very 100 and about 200 nanometers. And, you can see the size distribution is very good, according to this. I looked at the paper also. How do you prepare it? Again, this is binaphtile. Immediately, when you use binaphtile, of course, you can use it for various purposes. It also shows them interesting photoluminescence, right? So he derivatized it with a shift base, and then he, actually put in carboxylic acid, and then with he put in various metals, zinc, nickel, copper, and everything, and yellow is pyridine or water. He made it. This is a metalloligand, right? This is a metalloligand. It's a metal-containing ligand. It has got 2 carboxylic acid that can be linked various ways. What he did was adding metal acetates to this, different types of metal acetates, And this is in pyridine, and he started adding methanol to that while stirring. So, when it forms one-dimensional coordination polymer, immediately because of the anti-solvent that he added methanol, it started precipitating. So he standardized that, and he found out that it depends. The color changes with different types of anti-solvent that he used. Instead of methanol, he used various different types of solvents he added, and then showed that the color changes very nicely. And also it's all spheres, amorphous spheres that he got. And he said, see, one can use this kind of coordination polymers for different, to show some interesting photoluminescent properties. Just by changing the metal ions, you have the ability to control the color and luminescence and everything. That's what he says. This is a color, that make sure that this is a color. Okay, normalizing everything. Yes, it's a UV spectrum. It is not a photo. It's also emissive anyway, depending on what you have it here. So this is another one. So you may be able to make a lot of, people started making after this a lot of microspheres. In fact, we ourselves made a lot of gel and not nanospheres, nanofibers we made. Okay, 2D and 3D. Okay. Okay, what can you use apart from showing interesting luminescence? And Bin Lin is the one. I think I showed his photo yesterday. He was working in those days on NLO properties, by making a lot of non-centrosymmetric diamondoid kind of network structures. And now he's working on different type of fields. One is drug delivery. How you can use it for drug delivery. It's very simple. Okay. So he wants to deliver cisplatin, and then he made a derivative of this with succinic acid. So he took this. I just call it as a rod. I mean, he calls it as a rod. Okay. Then he put in terbium salt, and then he put in terbium salt, and then he started, in water, the aqueous solution. And then he added, again, different types of anti-solvent. In this case, diethyl ether. And the rate of addition, in the previous case, the microspheres by Chad Mirkin, and this one, the size and, distribution depends on the rate of addition and rate of stirring. Okay, they control it. In this case, they try to, this is in water soluble compound. Actually, this terbium-2, this ligand 3, stoichiometric ratio they form, and they pour solvent, because when you just mix it up and leave it, you will get crystals. They don't want crystals. They added diethyl ether and stir it at a very high speed, and then depending on the rate of addition of this anti-solvent, they started getting some cloudy thing. They centrifuge. They show that they're all, of course, before that, they need to adjust the pH, to find, using dilute sodium. I mean, that's experimental details anyway. So when they make it, they got some nanospheres, but they are highly soluble in water. You can't just like that use it directly, because once you take it, dissolves. It has to deliver where it's needed. So it has to go through. So they want to make it less soluble, because these things are, not soluble in, hydrophobic solvents. You can disperse them, those crystals not soluble. But in biological sense, you have to use, water, aqueous solution. So they're soluble. They want to reduce the solubility by putting silica coat. They put, this is a common thing they use it if you are working in nanoparticles. You will know that you can passivate the surface or make it less soluble by coating with silica. For that, you use polyvinyl pyridone here, this compound, and then they use TEOS, tetraethoxysilane. Okay, and under these conditions, they try to make, it precipitates a silica that is coated very nicely. But they also use proper surfactants here to make it a little bit soluble. Okay, so they make this kind of silica coated nanoparticles, and then they use it for drug delivery. When it goes and releases, it nicely releases cisplatin to the target they have studied. So this is another way of using, whether it is using this kind of coordination polymer. In this case, you can argue, oh no, this is not coordination polymer, it's a nano, or microsphere that is responsible. Okay, fine. But it's a combination. People started using MOFs, coordination polymer, make it into small nanocrystals or microcrystals, and then they use it for different applications.
We are comparing nanoparticles here for drug delivery with MOFs. So in previous slides, why can't we say that the color shown by the those tiny spheres was due to quantum dot effect?
Yes, they also discussed various things, but so I didn't go into the details of it. All right, I didn't go into the details. I mean, what they want to do under different, solving under different solution, and they show different colors. Okay, we can discuss about it if you are interested. Okay, what is the mechanism and what's it could be, because quantum, I don't know whether, this is about 100, 200 nanometers. I'm not sure.
Size is, I think, 1.2 to 10 nanometer size.
Yeah, I don't know. So maybe I didn't go through the mechanism of, what is the reason why it is doing it. Maybe.
Because we can use to synthesize the bit smaller spheres of MOFs and.
Yeah. Yes, true. And again, I mean, subsequent, he also made, he published subsequent paper in JAX, and where, I mean, I didn't go through it because this is the classical one, just to show that for the first time he made nano, microspheres and nanospheres too. That's what, according to him, says of this size. In all this science, nature, they don't explain everything. Maybe in JAX, I have to, we can discuss about it maybe later. Yeah, we will move it. Okay, so drug delivery. So after that, there's a lot of papers. Actually, he wrote a couple of reviews, very highly cited, Penderlin. Most of his reviews are highly cited anyway. So there is another guy here I just mentioned. Usually I give talks in US. So there's another guy from ChemEng. He's Huachen Zheng. He is an expert in making nano sized crystals of MOFs in various shapes and sizes. He will control. He knows how to control it. Okay, so he will make a smaller, very nice looking cubic crystal up to platy crystal, long needles, and control, by different experimental methods. So I'm not going to the details of it again. Just want to mention that there are a lot of papers, a lot of people working on this kind of making nano coordination polymers or MOFs for drug delivery. Okay, just want to highlight one or two examples. Okay, now we will move on to reactivity. You may wonder why reactivity, solid state reactivity here. We always look for crystal engineering, principles to understand how to control the physical and chemical properties. So we have seen so far physical properties. We haven't seen the chemical properties. There are so many chemical properties, including stability, including solubility. Chemical means it has to react, right? So how to control the reactivity? That's also, so make it reactive or make it passive, no reaction, very stable. So these are the things, people are interested in. So I'm going to talk about the chemical reactivity today. So if you go back to the literature, Aristotle, is the one against doing any reaction in the solid state. You know why? If I ask you to make a compound, what do? I said, okay, you need to make a urotropin or whatever we discussed. Okay. So immediately you look for suitable chemicals and solvent. Say no solvent. Say what? Because you try to explain to me, saying that only in solvent molecules can, move around the movement, and then they collide with each other. And when they collide at a particular transition state, the reaction occurs, and then you get the product. If you have compounds in the solid state, what do? They are stable, highly ordered. There's no movements. And are you kidding? Even if you grind them and mix them and heated them, what will happen? It decomposes many times. So you'll be against it if I say that, oh, don't use solvents because. But this is what was realized by Aristotle a long time ago. But later, people started asking questions. I will give a talk maybe later, but just want to say that one can do chemical reactions if the reactive functional groups are already, arranged very nicely to undergo chemical reaction. Then it's a matter of stimuli, external stimuli like heat, light, other things can do the reaction. So that's what we need. So in the solid state reactions, you don't have to mix two different things. Okay, that's another thing I'm going to talk about. It's a grinding, mechanical grinding, or ball milling. Those things are known, very well known. Now it's a big field by itself. Even the same one kind of compound, a single component, okay, one crystal that contains only maybe co-crystal. They're all joined together, not a mixture of two different material. So if you take that, you can make it to react, to react. How do you make it react? There are so many ways you can do. By heating, solvent removal, heating not up to the level of decomposing. There's no control on that. It's not selective. Okay, many times you just brutally you heat it up. Some of the metal, metal complexes, you heat it up to very high temperature brutally. Everything, all the organic moieties will go away. You will get metal oxides, metal sulfides, metal cellulose. All these things you can get it. But in this case, you are doing it selectively, not brutally, but selectively. And uptake, exchange, mechanical stress. Okay, all these things you can do. There are many reactions you can do this way in the solid state. Right from substitution, replacement of molecules, and that will lead to change in the coordination geometry and coordination number, even oxidation state. You can do change in oxidation state, conformational change of the structure, functional group replacement of the backbone. We have seen on the day PSM, SAIL, post-synthetic modification, SALE, SAIL, kind of thing. So sometimes it will also lead to complete change in the dimensionality in the structure. So a lot of things you can do with a single component, one crystal. And but by the way, you can also change the color, optical, and magnetic properties by doing so. But what is hindrance here is the maintenance of the single crystal. Because whenever you're dealing with coordination polymers, it's not like you can dissolve it back and determine through NMR, because if the alignment, if the arrangements or the connectivity, changes, you want to follow that, after doing this kind of solid state reaction. So the best way is to have a single crystal. If you don't have single crystal at the end of the reaction, then it's difficult to do. There are various other ways. You can do powder XRD, or you can do solid state NMR. Yeah, there are various ways of following, but the easier way is to have a single crystal at the end of the reaction. That's what we normally want, but this won't happen. But if it happens, then we call it as single crystal to single crystal reaction. Then it's easy for us to characterize. And then chemistry-wise, if there's a change in the molecular structure, of course you can dissolve it and do NMR, IR, and other spectroscopy, including UV, all these things to characterize what happened to that molecule. But it's very difficult to find the connectivity, because the connectivity is already disrupted by dissolving it in DMSO or DMF, or heating it up to to make solution for different measurements. Okay. Okay, what do we do in that case? Okay, take a look at it. I talked about it yesterday. So this kind of structural transformation, the previous one, when you do a chemical reaction, structurally it will be transformed. But that one, due to chemical reaction, bond breaking, bond forming. This type of structural transformation, there is no bond breaking or bond formation. It's a structural transformation without any disruption or without any breakage of bonds. I mean, even sometimes you can remove the solvents and it started breathing, what we call breathing MOFs. Actually, I had a model. I didn't bring it from Singapore. I just bought it in Korea. It's a kind of tinker, a toy. You can just make it bigger and smaller. But I forgot. So this is completely different. There's no reaction, but there's a structural transformation. Thank you. So in my slide, in my PDF slide, I have given a lot of write-up, for you to follow anyway. Sometimes I remove, sometimes I don't. So it's kind of messy. So usually I put in everything there in the thing so that even in the absence of my lecture, you should be able to follow by reading it. Anyway, how structural transformation can occur just by heating? It's coordination polymer. One example. This one is a zigzag type of one-dimensional coordination polymer with zinc chloride bipyridine. Very simple system. Okay, this forms zigzag type of structure. If you take a look at this packing, you see the chloride from the adjacent strand is closer to zinc. This is tetrahedron. Okay, so take the single crystal and started cooling it. If you started cooling it at below 143 minus 143 centigrade, it undergoes kind of structural transition. Usually it's different from phase transition because there is a reaction occurs. It forms a ladder. Can I call it ladder type of polymer? Because now the all the chlorine atoms are bridging. Okay, it forms a 2D sheet. Because of the bridging, the coordination number increased from 4 to 6. So if you take this compound and heat it back, it goes back. So it's a very simple one. Simple reaction is because of the terminal and bridging nature of the chloride ligand. As long as you have packed them very closely, the reaction will proceed. Can even think about additional thing to, this was published in, long time ago. So you can even think of new design, how to make different things to undergo this kind of structural transformation. This is very, very interesting. So just by heating, you can change the structure, make it chemically react. It's a reaction anyway. Whatever you say, the formation of bridging, it's a new bond is formed here. Okay. Next one. Yeah. This is another one using 2+2 cycloaddition reaction. I think I gave a very brief introduction day before yesterday. So you can do the 2+2 cycloaddition reaction. By the way, I'm taking all these examples from the textbook. Okay, I'm not. Sometimes if I give something new, that is due to the nanospheres and everything. Although I might have discussed, I might have added a lot of new things here. So these are all from the textbook. Okay, solid state cycloaddition reaction, involving coordination polymer. So this one is again another zinc compound. This is the trifluoroacetate. This is acetate compound. This is bipyridyl ethylene. It has got a double bond here. There's a pyridyl, 2 pyridyl groups with CH2 here. It forms nicely a ladder or railroad, whatever you call it, type of structure. In this polymer, the double bonds here are nicely aligned in parallel. The distance is about 3.7 or something. It's well below 4 angstrom. and you have got infinite pair of these olefin bonds. They can undergo photoreaction, 2+2 photoaddition reaction. Not only that, you see they are stabilized by pi-pi interaction, mainly through pi-pi interaction, or forced to have pi-pi interaction because of the bridging nature of this. That's easier ways. Otherwise, you will get, you need to use this kind of bridging ligand. When you have this compound, when you put it under UV light, it may be sunlight, or it can be mercury, or whatever you have got, special UV lamp. It undergoes reaction, photoreaction. You get this product. It's a colorless one, and it changes very light yellowish or creamish color, still maintaining the transparency in everything. When you determine the crystal structure, you see that it's all chemically transformed. So this gives a lot of idea. Okay, one can do really this kind of chemical reactions with 2+2 cyclization reaction. Okay, so instead of acetate, you can think how you can use a simple bridging ligand, nitrate, even chloride can be used. There are so many. Okay, I don't want to restrict your imagination. What kind of bridging ligand that you can use to bridge the strands, coordination polymeric strands containing photoreactive double bonds, ligands containing double bonds. Okay, so and also this one you can incorporate this coordination, the railroad type of thing you can incorporate into 2D morph or 3D morph. You can do a lot of things, right? Okay, this is another example, very unexpected. Solvent. How a solvent can influence the movements of molecules. Okay, there's no single crystal to single crystal studies involved in this reaction. This is a simple one-dimensional coordination polymer with silver, with bipyridyl ethylene, and it has got water, aqua ligand bonded. And you also have very weak interaction with acetonitrile. Okay, this is the way it looks like, because you've got CF3 is nicely hydrogen bonded to water. This is the way it forms. It's a one-dimensional coordination polymer, but forming weak interaction on across, and then forming a two-dimensional aggregate. So when you take a look at the packing, the silver distance is too far away. But don't look at this way. Even the next in front of you, in front of the screen, the distance between silver or the double bond is too far away. It's about 5.2. The minimum distance is 5.2. You would expect that it will be non-reactive, right? But if you take this compound and just leave it on the table, it loses solvent very easily. Even aqua ligand is gone, and acetonitrile will be gone, and then the non-bonded trifluoroacetate will coordinate back. We get, if you take a single crystal and leave it, next day it becomes powder. Okay, it's very difficult to analyze. Okay, you can analyze and see that the solvents are gone because it doesn't have single crystal. You think that, okay, how am I going to know what is really happening? But this compound is photoreactive. Whatever, the powder you got after removal, and then you started analyzing that compound. That's photoreactive, undergoing 2+2 cyclization reaction. So you can make this compound independently. You can make it independently, photoreactive one, and then you can compare with the powder and show that this is an interesting reaction. I won't say reaction. This is not a reaction. Transformation, structural transformation that highlights the movements of the coordination polymeric strands closer to each other, forming this type of photoreactive glider type of structures. So in the absence of absence of single crystal. So one can also, find out what is going on using other techniques, including photoreaction. So there are a lot of photoreactions nowadays. Is there anything else I have? Next slide. Yeah, it's a different one. So people started using it for two different purposes. Who are interested in 2+2 cyclic addition reaction, they apply to all these MOFs, and also they make it reversible. They make it reversible. What's so special about reversibility? Many of these compounds show interesting luminescence properties, and then when the cyclobutane ring is formed, because of that, there's no conjugation and there's no emission. So because there's no emission, they started on-off sensors, and they want to use it for optical storage. If it is reversible, you can use it for various applications. That's what people started doing it, and they started applying it to various systems. Okay, that will be another thing. Here I'm going to show you another interesting reaction that was reported a long time ago. It's another very interesting to my heart. That's why it's also described in the textbook. This is another coordination polymer. I won't say it's a MOF because it's one-dimensional structure. It's cobalt. Cobalt has got a bipyridyl group. It forms 1D strand here. And it has got two water molecules, two thiocyanate. Okay. And in addition to it, you have got a lattice bipyridyl group in the crystal, okay, which is not non-coordinating. Okay, between the two strands, it is nicely placed. This nitrogen pyridyl group is hydrogen bonded to water. That's what you expect. Weak interaction. All right. This is what happened. This extends, forming a 2D sheet. It's an aggregate. On one direction, it is coordination polymer. In the other direction, it is a hydrogen bonded aggregate. Right.
Excuse me. There's this one on leave. Maybe you can slowly.
Yeah. Please go. Yeah.
No, you can slowly wind up so that they wanna leave actually. They have an exam now after this.
Oh, okay. This is the last one then. This is the last one. Okay. Oh, exam at 9:30.
This is like a.
Okay, no problem. So what happens if you have this compound? If you heat it up, you see this is very close to each other, right? So this cobalt to nitrogen distance is about 5 point something, 5.4 or something, I don't remember. But it's very close. If you heat it up, what will happen? You can knock off the aqua ligand. When it's knocked off, then the nitrogen can go very close to cobalt and form a new bond. That's what happened. If you heat it up, water is lost. The water that is coordinated is lost. And what you get is a two-dimensional structure. So by removing solvents, you can make, actually, the paper describes, they also prepared this one independently. Again, this is not a single crystal reaction, but they prepared it independently. And after they got the powder, they showed by powder, various other ways, they showed that this is the same compound. So you can do reactions, in fact, in the solid state. A lot of interesting reactions. We can talk about it. So I think I will stop with this and let you go and write exam.